Okay, this is section 4.1, part 5. These will be the last ones. So in this section, in the 37 through 42 problems, it says identify the critical points and determine the local extreme values. So this time I'm not really worried about the global extreme. I just want to pinpoint all of the possible locations where we have a minimum or a maximum. This still does include endpoints, and so I've already gone through on all of these problems and considered the domain, which helped me determine whether or not there was endpoints to check. So on the first one, the domain is all real numbers, and so it has no endpoints. So now I just need to find my critical values. So I need to find the derivative, and I have to do a product rule. And so I get 2/3 x to the negative 1/3 times x plus 2 plus x to the 2/3 times 1. Alright, and so now I'm going to clean this up briefly. This drops to the bottom, and so it looks like I have in the numerator 2 times x plus 2 over 3 times x to the 1/3 plus x to the 2/3. Okay, I am a big fan of putting these into fraction form because then it's easier for me to quickly tell when it's equal to 0 and when they're undefined. So other people have different styles, but this is what works for me. So I need to get a common denominator and add these together. So this guy's going to need a 3x to the 1/3, and the other one doesn't need anything at all. And so that's going to give me a denominator of 3x to the 1/3, a numerator of, I guess I'll distribute that to 2x plus 4 plus 3x to the same base, add the powers, 2/3 and 1/3 is 3/3 x to the first. And so my derivative is 5x plus 4 over 3x to the 1/3. So now I can quickly see that the derivative equals 0 when 5x plus 4 equals 0, which should be x equals negative 4/5, and the derivative is going to be undefined at x equals 0. So now I'm going to do a sign chart. I'll move over here for the sign chart of my derivative because I want to know what the slopes are doing on each side of those values. I already know at those values the slope is 0. That's why I found them, or undefined, I guess. So now the question is what's happening in other places. So I plug in a number bigger than 0, like a billion, to my derivative. And in the numerator it's positive, and the denominator is positive. I plug in a number like negative a billion. I get negative on top. The cube root of a negative is a negative, so I get negative on the bottom. Negative and negative is positive. And then between the two, I need to plug in a number like negative a half. So now I got to pay a little more attention. Negative a half times negative 5/2 plus 4 should be positive. Negative a half, cube root is negative times 3 is negative. Positive divided by negative is negative. And so now I'm pretty much done because I don't want the globals. I just need to know what are the local max and mins. So negative 4/5 is going to be a local maximum because my slope is positive and then negative, saying I'm going up, and then I'm coming back down. And then x equals 0 is a local minimum because I'm going down, and then I go back up. Now the interesting thing about 0 is that was a place where my derivative was undefined, but it isn't because of a discontinuity or an asymptote like before, because 0 is part of my function. So what that likely tells me is I come down and have a cusp or a corner. And I'm not 100% sure which it is, and frankly I don't really care. I do know that it is not a vertical asymptote, it's not a problem with the domain. So that leaves you only 3 possibilities: a corner or a cusp, or a vertical asymptote. I know it's not a vertical asymptote, a vertical tangent line. I know it's not a vertical tangent line because my slope was negative and then it turned to positive. If it was a vertical tangent line, it would be something like going negative and then stays negative, slopes negative, slopes negative. But that didn't happen for us. So I'm guessing cusp. So this is the x values. The question says determine the actual local extreme values. So I need the y values that go with them. And you know what? I'm going to leave you to do that. So find f of negative 4/5 and find f of 0 to find the actual mins and maxes. Okay, so let's see if we can do the last bits a little bit quicker. This time I looked at the domain and I know I can't take the square root of a negative number. So if I use a number like 0, I get a negative, and that's bad. So I just asked the question, when is the inside equal to 0? And that was at 2 and negative 2. And a little quick checking shows me that I need numbers bigger and smaller than that. So I have a whole range of numbers that are not defined, which means probably I'm going to find, not probably, I definitely will find that the derivative is undefined in that same region. But I don't really care. Okay. So I've got endpoints, and I've already checked them. I plugged in negative 2 and positive 2 and got 0 for both. And so now I need to take the derivative. And I get 2/3 x to the negative 1/3 times the square root of x squared minus 4 plus x to the 2/3 times a half x squared minus 4 to the negative 1/2 times 2x. So I have some cleaning to do. Okay, 2 terms. That's in the numerator, 2's in the numerator, so I have 2 square root of x squared minus 4. And the denominator, I have a 3x to the 1/3 plus, okay, denominator, I have the square root of x squared minus 4. This is not looking pretty. The half and the 2 cancel out. So I have x to the 2/3 times x to the 3/3. So I have x to the 5/3. Okay, again, I really do prefer these in fraction form, which means I need a common denominator, which means, let's change color here, I need to multiply each of them by the other denominator. So I'm going to have to multiply by x squared minus 4, square root of, and then this guy is going to get the other denominator, so he gets 3x to the 1/3 multiplied top and bottom. Alright, so that leaves me with what appears to be a pretty ugly problem. The denominator and now let's look at the numerator. The square root of x squared minus 4 times the square root of x squared minus 4 is just x squared minus 4. Plus 3, and then I add the exponents and I get 6/3 x squared. So then my derivative, clean it up slightly. The bottom is still ugly. but the numerator becomes 2x squared plus 3x squared is 5x squared minus 8. Okay. So now let's look for critical values, and I'm sort of running out of room, so I'm going to jump up here and take a look. I better speed this up. I know that the derivative is only going to equal 0 when 5x squared minus 8 equals 0. Add the 8, divide by 5, and take the square root, and I get positive negative the square root of 8/5. And then I need to know when the denominator equals 0, and that's going to be at x equals 0. So these are the undefineds. So at x equals 0, the denominator has a problem. And at x equals -2 and +2, the denominator has a problem. But you'll notice I've already got those on my list. We'll add them here anyway. Okay, it's time for a sign chart, and then we will essentially be done, and this will give us all the evidence we need. Alright, so my critical values are 0, the square root of 8/5. I don't know what that number is, but I know that it is smaller than 2, and 2 was my endpoint, and -2 was my endpoint. So something interesting has happened on this problem. And that is why it is important to consider your domain. I have found 3 critical values: 0, positive -2, and positive negative square root of 8/5. And unless I've made a horrible mistake, which I'm not going to rule out, none of these values are of interest to me, because all of them are in the part of the function which I have already determined is not part of the domain. I'm only supposed to be looking for values between -2 and -infinity and 2 and infinity. So that means that everything here isn't actually a part of my function. So when I look at my sign chart, all I really need to do is look at my derivative and plug in a number bigger than 2 to find out if the slopes are positive or negative out here. So I go to my derivative and plug in a number like 100, and I quickly see that the top is positive and the bottom 100, it's still going to be positive times positive is positive. And then I plug in negative a billion or so, and I get on top a positive. On the bottom, I get the cube root, I get a negative. X to the, or a negative number to the 1/3 is negative times 3 times, plug in a number here and square it -4, it's going to be positive. So I get a negative slope out here. So based on the evidence I have so far, -2, 0 is going to have to be a local minimum, because my slopes are negative as I approach -2. And then out here at +2, I leave it with a slope of positive, and so that makes that a local minimum as well. So these are both local mins. Alright, so the only thing that occurs to me is I need to go back and just double check my math to make sure that I've found the right critical values of positive -8/5. I'm not going to do that because I'm running out of time, but graph this on your calculator and see if what you have matches what we've found. Alright. So now, I've already checked my domain on this one. It's between -2 and +2. Anything bigger than that would cause us to have a negative number. So let's quickly find the derivative and see if I can do this in under a couple of minutes. So I get derivative of x is 1 times the second plus the first times the derivative times negative 2x. So my derivative simplifies to negative, let's see, half and 2 cancel out, x squared, and the denominator is the square root of 4 minus x squared. I need a common denominator, so this guy needs the square root of 4 minus x squared top and bottom, which leaves me square root of 4 minus x squared is 4 minus x squared minus x squared all over 4 minus x squared. So when is the derivative equal to 0? Well, that would be when the numerator of 4 minus 2x squared equals 0. And when is the derivative going to be undefined? And that's when the denominator is equal to 0. And notice that's going to happen at negative 2 and positive 2. Already going to check those because those are my endpoints. And when is slope equal to 0? So I subtract 4, divide by 2, negative 2, and I get x squared equals 2. X equals positive and negative square root of 2. I put these on a sign chart. Negative 2 to positive 2. Negative square root of 2. Positive square root of 2. Alright, I plug in 0 into my derivative, and the numerator is positive 4. The bottom is positive. I plug in a number between square root of 2 and 2, like 1, and I get on top, I should have simplified this, but that's 4 minus 2x squared. Plug in 1, and on the top I get positive, on the bottom I get positive. I plug in a number bigger than 2, but I can't because that's the end of my domain. And it occurs to me that this is possibly going to be an issue, but we'll figure it out in a minute. Plug in negative 1, and I get a positive over a positive. Plug in negative 10 billion, and hey, what do you know? I get a, never mind, I'm not supposed to do that anyway. And so I have 3 positive slopes, which is interesting. And it occurs to me I must have made a mistake because this evidence is impossible. If I am at negative 2, 0, and later I'm at positive 2, 0, and it says here that my slope goes up until negative square root of 2. Then my slope goes up again until I get here, and then it goes up again until I get back down to 0, which is impossible. So somewhere in here I've made an error, and at 18.5 minutes of this video, I'm probably not going to find it real quick. My guess is that this slope should actually be negative. So let me just check real quick. 4 minus 2x squared, I plug a number like 0, I still get positive 4. I plug in a number and I get positive. Okay, so I'm going to have to do a little exploring, and it looks like we will have a part 6. I'll pick this one up in a minute.